Welcome to all. In the continuation of our discussion on stereochemistry, today I am going to discuss on a very interesting subject called asymmetric synthesis. Asymmetric synthesis is also called chiral synthesis. It's a branch of organic chemistry that involves the preparation of molecules in a way that ensures the resulting product is almost optically active. Optically active. So already I have explained in my previous lectures what is meant by optically active and what is the condition for the optical activity, and so many factors I have discussed in my previous lectures of stereochemistry. See, these are optically active compounds. They may be enantiomers or diastereoisomers. Both are optically active, and that is followed by the or that is subjected to the condition of the symmetry. If there is no symmetry elements, or if there is no alternate axis of symmetry, then that molecule, either it's an enantiomer or the diastereoisomer, is optically active. So for any detail you can refer to my previous lecture. So I don't want to prolong that part here also. And the enantiomers offers different biological properties. One enantiomer offers one biological property, a positive effect. Say it's a positive effect. The other enantiomer that shows a negative effect. Okay, so one must control the chirality of a molecule that are synthesis. So this is very crucial in pharmaceutical industries, agrochemicals, and other biologically active compounds. So in the today's class, I am going to introduce the optical purity. It is expressed in two terms, the enantiomeric excess and the diastereomeiric excess. Okay, and in the part 2, see the part 1, apart from the simple introduction, I will explain what are the methods that are available for the asymmetric synthesis, that is to obtain optically pure compound. But in the part 2, I will go for the applications. Applications of the asymmetric synthesis. Okay, let us go into the lecture. So before going into the lecture, already a number of times I have told, chemistry is a wonderful subject, and many scientists and philosophists, they just quoted some words about the chemistry. So Adam Sandler, he said, chemistry can be good and bad thing. It may be a good thing if you use for a good purpose, and a bad thing if you use that chemistry for the bad purpose. Chemistry is good when you make love with it, and the chemistry is bad when you make crack with it. And the famous Linus Pauling, his era is 1994. He said, every aspect of the world today, even politics and international relations, is affected by chemistry. is affected by chemistry. Such a wonderful subject is the chemistry. Wonderful subject is the chemistry. And today our discussion is on the asymmetric synthesis. In the world, maybe a million and billion or billions of dollars of dollar amount of money is spent in the asymmetric synthesis. That is, let us see why we are concerned about the asymmetric synthesis. That is, we need a optically pure compound. That is possible only in the by means of asymmetric synthesis. Asymmetric synthesis. Okay. So first of all, we must already I have discussed. Although I have discussed, I just introduced that the carbon is the one which is responsible for all the things. The carbon which has mass number 12 and atomic number 6, okay, which is responsible for all the things, okay, and a carbon is a fundamental block of life and chemistry. Without carbon, nothing will happen, especially the biological molecule, the biological system. Okay, so if you take the biological molecules, it may be a carbohydrate, vitamins, hormones, steroids, alkaloids, and whatever the things. Many biological molecules that is made up of only the carbon molecules. Okay, and the second one is the polymers. So nowadays the polymers plays a very important role in building up of many materials, especially the automobiles. Let us take automobiles or airplanes or anything. The polymer, what is the quality of polymers? It is lightweighted, hard, so that the mileage can be increased and the weight of the particular instrument is decreased and the mileage can be increased. And number 3 is a fossil fuel. So without a fossil fuel, we cannot survey nowadays. Lot of research is going on the hydrogen as a fuel and solar fuel, that is a non-conventional fuel, but still the fossil fuels plays a very important role. That is the petroleum, the kerosene, the oil, grease, etc. These are fossil fuels are all are carbon molecules. And a diamond, it's an allotrope of carbon. So it is used for mainly for a cutting purpose and ornamental purpose. And the graphite used in many applications. The simple application is a pencil. The pencil, the black rod that is in the middle of the pencil is the graphite, and in the a small battery, the graphite rod is there to make the connection, and carbon nanoparticles. If we decrease the size of the carbon, the nano size, a wonderful property is exhibited by the carbon. Okay, and because of this, we can say carbon is the king of the elements. So let us go for the optical purity. What is meant by optical purity? Okay, it is the dream of every synthetic organic chemistry. That is optical purity means, so suppose already I have discussed the R isomer and S isomer, D isomers and the L isomer. Okay, the optical purity means the 100% R isomer and 100% S isomer can be obtained. Okay, so the method of obtaining a 100% R isomer and 100% S isomer, we call it as optical purity. Optical purity. So this a small diagram that tells about how the difficult the preparation of the optically pure compound. Optically pure compound. One scientist just iterate or express his opinion to the other scientists that success, he created a drug that is effective, quick acting. That is true. That is no false. But it is expensive. At this point, it is expensive. So, the research is going on to prepare the optically pure compound in an inexpensive manner. So, that is the role of asymmetric synthesis. Asymmetric synthesis. So, first of all, we can define the optical purity. The optical purity is a way of describing the composition of a mixture of enantiomers. You can describe optical purity in terms of enantiomers or in terms of diastereoisomers. Okay. So, in terms of enantiomer, percentage optical purity equal to, that is a EE, enantiomers, okay, equal to the optical rotation of the sample divided by optical rotation of pure enantiomer into 100. That is optical purity. Optical purity. Okay. Sample optical rotation of the sample divided by optical rotation of the pure enantiomer. If it is 100%, it is 100% optical purity. It can be expressed in terms of enantiomeric excess, that's a EE, already I have told. The difference between the percentage of two enantiomers in a mixer. So, enantiomeric excess EE equal to concentration of R minus concentration of S divided by the sum of concentration of R plus S into 100 equal to percentage of R minus percentage of S. Okay. So, the optical purity is numerically equal to enantiomeric excess, but is experimentally determined. More the enantiomeric excess, more will be the optical purity. More will be the optical purity. Here it is a diastereomeiric excess. We have the one a ketone, a prochiral center is there. The C double bond O is a prochiral center. Already I explained the prochiral center. The next carbon is a chiral center. So, if you make the keto group as a chiral one, then what will happen? It will convert into a diastereoisomer. So, the ketone is subjected to a reduction using lithium aluminum hydride. It forms a alcohol, 20% of one isomer, one diastereoisomer, and 75% of another diastereoisomer if R equal to methyl. If R equal to tertiary butyl, so almost exclusively 98% of the second isomer, diastereoisomer is formed. So, in the first case, diastereomeric excess is 50%. The second case, diastereomeric excess is 98%, 96%. So, percentage of diastereomeric excess equal to major minus minor divided by major plus minor, which is equal to percentage of major minus percentage of minor. Okay. So optical purity. The word I am repeating this word. It's a wonderful word. Optical purity. Okay. So optical purity is in other words I can say it's enantiomeric purity or diastereomeirc purity. How one can obtain the enantiomeric compound, enantiomeric compounds. Okay. The first one is from natural products. From natural products. Nature is the one which can give a pure compound, pure enantiomeric. Okay. So we can say nature is a good chemist. Nature is a good chemist. And it gives a 100% enantiomeric excess product. 100% enantiomeric excess product. For example, amino acids, sugars, proteins, nucleic acids, vitamins, terpenes, alkaloids, steroids, etc. Okay. So other methods are available. Other methods are available. Okay. By resolution of recipe mixture. You know that what is meant by recipe mixture? Recipe mixture is the one which contains 50% of one R isomer and 50% of S isomer. Resolution is a separation of one optical isomer from the mixture. So in that 50% of the product will be lost. Product will be lost. Okay. And the second method is by using laboratory controlled enzymatic reactions. But the most effective method of synthesis of enantiomeric compound is the asymmetric synthesis. It is the most effective method. There are so I can define what is meant by asymmetric synthesis. Asymmetric synthesis is a chemical reaction or a reaction sequence in which one or more new elements of chirality are formed in a substrate molecule and which produces the stereoisomeric. It may be a enantiomeric or diastereomeiric products in unequal amounts. So in the previous case I have shown not not 100% one product is formed. 90% one product is formed, 5% another product is formed. Okay. So it is produced in unequal amounts. So we have the asymmetric reaction here. We have the astrophenone. You are targeting the prochiral center carbonyl carbon by the chiral carbide, hydride ion. It produces the S isomer of 97.5% versus the R isomer 2.5%. If we calculate, it comes the enantiomeric excess come into 95% enantiomeric excess. Okay. So here the carbonyl center is the prochiral center. Prochiral center. This is also called stereoselective synthesis because it is formed, two isomers are formed in unequal amounts. If one isomer is specifically formed, it is stereospecific reactions. But if two isomer is formed, one isomer is predominant, it is a stereoselective reactions. So reciproc reaction here, we are having the same compound, the astrophenone, when reduced with sodium bromohydrate, 50% of S isomer and 50% of R isomer is formed, and as a whole that mixture is optically inactive, not like in the previous case. The second case, if one of the product forms exclusively, that is 100% enantiomeric excess is observed, that the reaction is called stereospecific. So here some schematic diagram. A plus B gives C plus D, which is a pair of isomers. C and D is formed in unequal amounts. We call it a stereo selective. And C and D are diastereoisomers. We are called it is diastereo selective. And C and D are enantiomers. We call enantio selective. If only C or only D is formed exclusively, then the reaction is called stereospecific. So let us see the methods of asymmetric synthesis. There are four methods are available. One is the chiral pool method, the chiral auxiliary method, the chiral reagent method, the chiral catalyst method. First of all, we go into the chiral pool method. Chiral pool method. Pool means like a swimming pool, like a swimming pool. Plenty of pure enantiomers are available. Where it is available? It is available in the nature. It is available in the nature. Simplest and oldest approach for asymmetric synthesis. So the chiral pool method is the simplest and oldest approaches for asymmetric synthesis. Okay. It uses an enantiomeric pure natural product as a starting material. As already told, the starting material is a enantiomeric pure natural material. What is mean by a chiral pool? What is mean by a chiral pool? The chiral pool is nothing but a nature's ready-made chiral centers. That means the pure natural products, usually amino acids or sugars from its pieces containing the required chiral centers, can be taken and incorporated into product. So whatever the things available in the nature as a pure enantiomer, that is taken and it is manipulated to give a pure product of our interest. Common chiral starting materials derived from nature include amino acids, chiral carboxylic acids and monosaccharides. So we have the natural L amino acids, alpha hydroxy acids, natural D sugars, L series and S lactic acid, D repose. So these are all small examples. These are all small examples. The second method is a chiral auxiliary method. Auxiliary means so whenever you need, you can attach to the substrate, and this auxiliary just direct the incoming group where to attack, thereby making one product predominantly formed than the other product. And finally, this chiral the auxiliary is removed. The chiral auxiliary is removed. Are you follow my point? So deliberately we are attaching this chiral auxiliary to the substrate, okay, and the reaction is performed. It forms a predominantly one product than the other. Finally, the auxiliary is removed. An enantiomeric pure compound usually derived from a simple natural product like an amino acid called a chiral auxiliary. So here chiral auxiliary is a natural product like amino acid is attached to the starting material. A diastereomeirc selective reaction is carried out, which because of the enantiomeric purity of the chiral auxiliary gives only one enantiomer of the product. The chiral auxiliary is removed by, for example, hydrolysis, leaving the product of the reaction as a single enantiomer. Okay, most of the cases the single enantiomer is formed. In some cases, it may give a mixture of enantiomers with a high enantiomeric excess. High enantiomeric excess. The best chiral auxiliaries can be recycled. So although stoichiometric quantities are needed, there is no waste. Stoichiometry means if you take 1 mole of the substrate, 1 mole of auxiliary is needed. But if you used that, so it is so costly, so costly. But if you use, you can recycle it, recycle it, and you can use it for another reaction. So no waste is that. No waste is that. Okay. So here is a schematic diagram. The substrate which is achiral, and the chiral auxiliary is there. And the first step, it is attached and form a substrate chiral auxiliary addendum, and a stereoselective reaction is performed. Okay, it forms a product, and it is hydrolyzed to give the pure the product, chiral product, leaving the chiral auxiliary, The best example, the alkylation reaction with the valine derived chiral auxiliary. Here we have the chloroketone and an amino acid. So amino acid is a chiral amino acid. Okay, the valine chiral amino acid, it is attached to the keto compound by using the a mild base triethylamine, and the chiral the addendum is formed. And the second step, the reaction is performed by using a strong base called lithium diisopropylamide, and the alkylation is carried out by using the ethyl iodide. So here the 94% of one isomer is formed than the other isomer. Other isomer is formed only 6%. And finally, the auxiliary is removed. Okay. See, let us see the 95% is formed predominantly than the other isomer. The third method is a chiral reagent method. So we can use the chiral reagent instead of the chiral auxiliary or the chiral pool. Okay. The formation of the new chiral center is induced by a chiral reagent intermolecularly. Here we have the prochiral ketone, and by using the chiral boron hydride, we'll get a 99% yield with a 97% enantiomeric excess. That is a reduction of achiral ketone by chiral boron hydrate results in chiral alcohol. And the final one is the chiral catalyst method. The formation of a new chiral center is induced by chiral catalyst. So the enantiomeric catalysts are chiral coordinate compounds. So these catalysts are coordinate compounds has the ligand of chiral character. That is, ligand shows a chirality. Example is a pinap and the binol. The binaphthyl compound or the binol. So here is the example of a binap and the binol. Okay, the diphenyl phosphine compound. So here we have the restricted rotation. Because of that, it shows optical activity. Using this chiral catalyst, one can produce a chiral compound of enantiomeric pure chiral compound. So this is an example for this step used in the chiral catalyst method. Sir, if you are having any doubt, you can ask me in my comment box. So always I welcome your comment that will encourage me. I request you to subscribe my channel, like my videos, share my videos, and if you want to put any other topic in chemistry, you just write in comment box. I will give video lecture on that topic. Thank you very much. Thank you.